Assuming the values in section 12.5.3, what is the maximum distance above the surface can the loose ends of the chains be, assuming a brush conformation? What is your estimate of a realistic average distance? So, if we look at section 12.5.3, we see that a solution of polystyrene has a molecular weight of 200,000 grams per mole, saturating a colloidal surface. Weight increases show that there is a 2.5 milligram of polymer per meter squared of surface. Since this is polystyrene, each mole is so there are 8 carbons. So let's find out the molar mass of a mer. Eight times 12 carbons is 96, and there are 8 hydrogens, so it is 104. So molar mass of a mer is 104 grams per mole. Density of polystyrene we know is 1.06 grams per centimeter cube. Volume occupied per mole of mer would be 104 grams per mole over 1.06 grams per centimeter cube, which is 98.1 centimeter cube per mole of mer, which is equal to 98.1 times 10 to the negative 6 meter cube per mole, because 10 squared centimeter is equal to 1 meter. So 1 meter cube would be equal to 10 to the power 6 centimeter cube. So 98.1 centimeter cube per mole will be 98.1 times 10 to the negative 6 meter cube per mole. Volume occupied per mer would then be 98.1 times 10 to the negative 6 meter cube per mole over 6.02 times 10 to the 23, the Avogadro's number, mers per mole, which is 163 times 10 to the negative 30 meter cube per mer. So this is the volume occupied by 1 mer. Since we know that there is 2.5 milligrams of polymer per meter square, let's see what this translates, what this volume translates in terms of meter squared, that is the surface area. For that, let us assume that the space is a cubical space of unit length, and you have these polymers are in the form of a train or pancake, and then there are some loops, and then there are some brushes or tails. Okay, so these are the tails or brushes, and these are the loops or the mushroom and this is the tail or the train or the pancake. So let's see, there's so much of all that on the surface. Okay. Now we want to find out the length of this tail, how much this tail is jutting out of the surface. That's what we want to find out. Or the length of the brush, the maximum length of the brush. Let's see what this volume translates to in terms of meter squared per mer, assuming that all this is 1 unit length of a cube. We can say that 163 times 10 to the negative 30 meter cube to the power 2/3 per mer will be the area that it is occupying. Okay, and that comes to cube root of 163 is 5.46, and square of that, the cube root of 163 is 5.46, and if you square 5.46, we get 29.84. Cube root of 10 to the negative 30 is 10 to the negative 10, and if we square 10 to the negative 10, we get 10 to the negative 20. So we have 163 times 10 to the negative 30 meter cube per mer to the power 2/3 is 29.84 times 10 to the negative 20. Or 2.984 times 10 to the negative 19 meter squared per mer. So now we have how much surface area is actually covered by the polymers, which is 2.984 times 10 to the negative 19 meter squared. So 1 meter squared has 1 over 2.984 times 10 to the negative 19 mers, which is 3.35 times 10 to the 18 mers per meter squared. Let's convert this to the mass in grams. We'll get 3.35 times 10 to the 18 mers per meter squared over the Avogadro number 6.023 times 10 to the 23 mers per mole times the molar mass of a mer, which is 104 grams per mole. So this gives us how much mass which is 5.79 times 10 to the negative 4 grams per meter squared, or 0.579 milligrams per meter squared. We can now compare this with 2.5 milligrams per meter squared of polystyrene. Since there is 2.5 milligram per meter squared of polystyrene, as we know, the fraction of polystyrene that is bound or that is in the form of a train would be 0.579 milligram per meter squared over 2.5 milligram per meter squared, which is 0.23. So 0.23 is the bound fraction, or the fraction which is in the form of a train or pancake. Let's go back to our picture. So this part, which is the train or the pancake, is 0.23, which means 1 minus 0.23 should constitute the mushroom and the brush forms. Let us assume that there is no mushroom form for our convenience, and everything that is not train is a brush. That there are only train and brush forms. So we are making this unrealistic assumption for our convenience. So if we do that, we can get 1 minus 0.23, which is 0.77, is the fraction of brush form. Our goal is to find out the length of this brush. The length of this brush is our goal. The 0.77 that is in the brush form, let us find how many moles that will constitute. Let us find out the molar mass of the brush form. Since the total molar mass is 200,000 grams per mole, that times 0.77 would be 154,000 grams per mole. So 154,000 grams per mole is in the brush form. And we want to find out the length of this. Since molar mass of a mer is 104 grams per mole, we can find out how many mers are in this. So 154,000 grams per mole divided by 104 grams per mole, that will give us the number of mers, which is 1,481 mers. Now we can find out the length of 1,481 mers. So polystyrene is like this, CH2, CH, and it has a phenyl group, and then you have a CH2 and then CH group, and so on. And this can be atactic or isotactic or syndiotactic, as the case is. Okay, so this is the structure of polystyrene. In this example, we have 3 mers, and we see that for 3 mers, there are 1, 2, 3, 4, 5, 6 carbon atoms, and there are 1, 2, 3, 4, 5 bonds. Okay. If we have 2 mers, then one, two, three, four carbon atoms and 1, 2, 3 bonds. So we can see that the number of bonds is 2n minus 1, where n is the number of mers. Now, the distance between a carbon-carbon bond is 1.4 Armstrong. In polystyrene. So we can say that the distance between two n minus 1 bonds would be 1.4 times 2n minus 1 times, if you see, this is not linear. This is not a linear chain, but it is zigzag. And carbon is sp3 hybridized here. The bond angle is 109.4 degrees approximately. So the length of the length of 2n minus 1 bonds would be 1.4 times 2n minus 1 times sine of 109.4 over 2, because this length is given by nd sine theta by 2, where d is the bond length, n is equal to number of bonds, and theta is the angle of carbon. Okay, so we have 1.4 Armstrong times 2 times 1481 mers minus 1 times sine of 109.4 over 2. (3,383 Armstrong). So this is the maximum length of the brush. So this is the maximum length of the brush, and this is making the assumption that anything that is not in the bound form or in the train form is sticking out as a brush. But realistically, there could be some forms that are loops, as shown in this picture. There could be some loops besides the train form and the brush form. So let us make some realistic assumption and say that 50% of the remaining is in the brush form and 50% is in the loop form or in the mushroom form. So bound fraction was 0.23, and so the remaining is 1 minus 0.23, which is 0.77, and this time let's say that 50% of 0.77 is in the loop form and 50% of this is in the brush form, which means 0.77 over 2, that is 0.385, is in the loop form and 0.385 is in the brush form. Now let's find out the length of the brush. So out of 200,000 grams per mole, this time 0.385 is in the brush form, which is 77,000 grams per mole. Let's see how many moles are there in this. So 77,000 grams per mole divided by 104 grams per mole will give us the number of moles, which is 740 moles. Now let's find out the length of 740 moles. So we just saw that the distance between carbon-carbon bonds is 1.4 Armstrong times sine theta by 2, which is sine 109.54 over 2, and that times the number of moles, which is going to be 2n minus 1, or 2 times 740 minus 1. This gives us 1690 Armstrong. So the realistic estimate of the length of the brush is 1690 Armstrongs.